For my walkthrough of Vulkan, I'm going to be using GLFW. As described on the wiki page, GLFW is a lightweight utility library for use with OpenGL, OpenGLES, and Vulkan. It provides programmers with the ability to create and manage windows as well as OpenGL and Vulkan contexts, as well as handle joystick, keyboard, and mouse input. Okay, so for this tutorial, I'm going to assume you know what makefiles are, you know how to use them. You have some understanding of Algebra 1, Algebra 2. You know how to program in C. You know how to include libraries in C. And that's pretty much it. I will add the disclaimer that there's going to be more things that I'm not going to go fully in depth in, and that'll be up to you to look into those things more yourself. If you're curious about where to install the SDK for Vulkan, if you go to vulkan.lunar.com, you can walk through this and install the files that you need. So, with that out of the way, I'm just going to make my main.c file. I'm going to step into Vim here. And what we're going to do is we're going to include the vulk.h header along with defining the vulk implementation. Normally, what people do is include vulkan.h. But in our case, for simplification, we're not going to do that. So Vulk simplifies the process a little bit more. It allows you to dynamically load entry points required to use Vulkan without linking to vulkan1.dll or statically linking to the Vulkan loader. What a metaloader is, it's a library designed to manage the loading of function pointers for like a specific API. So normally when you write a Vulkan program, you need to call functions like vk create instance. However, those functions don't actually live inside your program. They live in a system file like vulkan1.dll on Windows. I don't know if it's, well, it wouldn't be a DLL file on Linux, but anyways, you get the point. Vulk changes how your program finds and talks to those functions. Here I have my make file, and I just did a simple hello world in my main.c. In my my make file, I have the path to, they have the include path for the SDK. And then from that include path, I also have the path where the Vulkan headers are. So I have -i, the Vulk path, which is where the include files are, /Vulk. And this is the files, again, I got from the SDK at the Lunar website. And then I have my pkj config for GLFW3 and Vulkan, so I can get the proper flags needed to compile for GLFW and Vulkan. And then I have my recipe and then a simple clean. And I didn't completely finish this. There's actually a little bit more I have to do here. So I need include the flags. So there we go. Those are our flags, and I'll include this at the end. And I made a little mistake here and called this make when I'm going to call this main. So now the output will be main. And I'm just going to build and run and see how it works. I'm going to do a make clean first because I think I already built it. Whoops. Make. And then see if we can call main. And it works. Okay, so I added a little bit more to our make file. I just have a simple helper macro to help us print errors and show the line number it happened. And you can also add a string to it to describe what the error was. This is just to help us out. In the future, when your program gets longer, you're going to really want to know what file the error came from and what line. So just a helper function. Then we have the initialization of GLFW. Here we tell GLFW basically just give me a blank window and a native window handle. And that we're going to handle the graphics part ourselves. By default, GLFW assumes you want to use OpenGL, but that's not what we're going to do. And right here, this was just a test to see if the print error function works. That's why I wrote this here. If you were curious about this, no. Here, we create a GLFW window set to the width and height. We give the window a name. We initialize Vulkan. And I'm going to get rid of this. It's not needed. All right, so right here, we're trying to determine the maximum version of the Vulkan API supported by the loader. And we're trying to make sure that we can interface. We're going to make sure that we're going to try to get an interface that we want. So here, we're just using VK enumerate instant version. And all this does is give us a instance version, which if you wanted to look at this, basically this is a number and we have a bit mask to tell us the major, minor, and patch version. And this bit masks it or does some bit masking for us to get those values for us. And really, I should be doing something like this, just to make sure that things are going smoothly. And I'll do classic one of these and say could not get instance version. Then after that, we just simply destroy the window and exit and terminate GLFW. And if we build and run our program, we get the maximum version the loader supports. And there is something else I do want to mention. So before we keep going, whenever you do something in Vulkan, and I've kind of brought this up briefly, is that Vulkan you have to look for the function pointer for the function you want to call. And there's a difference between function pointers. There's instance level pointers and there's device level pointers. The instance level pointers, they handle tasks like querying physical device properties, creating surfaces, or picking a GPU. So those are like some examples of what a device pointer might look like. Like it might look like a function like this: VK create instance or Vulk load instance. When you see those, what's following will be instance level pointers. And then there's device level pointers. These functions are tied to a specific VK device. You can get them with Vulk load device. Then basically the functions you get use after that are going to be device level pointers. It's a logical connection to a specific GPU. Another thing I want to point out is that I am using C89. And as you can see in the makefile, and the way I wrote the print statement doesn't technically strictly follow C89. So if you want to change that and make it a way that is more closely following C89, you can do that if you want. But I have C89 because that's what Vulk uses. Okay, so now we're just gonna simply make a window. And to do this, I'm gonna create a VK instance and a VK surface variable. Also, I'm removing some of the printing statements that were here that printed the version. And instead, I'm going to check for a specific version of Vulkan. We're going to want to stick with at least version 1.3 because in the future, we're going to use dynamic rendering. And dynamic rendering needs at least this version. Below that, we're going to create an app info struct. And we're also going to define extension count above it, the extension count variable. A lot of Vulkan structs, I believe all of the Vulkan structs, will have this S type. The S type basically tells Vulkan what kind of struct is this. In this case, we're telling Vulkan that this is a type application info struct. Then we have the name of the application. We also have the application version. This is a developer supplied version number, so you could put whatever you want here and it's not going to affect the application. It's just for you to look at. Then we're going to have an API version. We must use the highest version of Vulkan that the application is designed to use. In this case, we want to use 1.3. Next, we have the glfw get required instance extensions. This function returns an array of names of Vulkan instance extensions required by glfw for creating Vulkan surfaces for glfw windows. And then if it's null, we'll say that we couldn't get the required glf extensions for the glfw window. Next, we're going to do a vk create instance. This is going to make our instance function pointers. And we should check to make sure that it's not equal to vk error layer not present. And if it is, we'll do, another printf statement. I'll say cannot use instance function pointers. There we go. And I made a little mistake here. I'm going to have to set this to equals to and not equals to. If it's equal to an error, then we know there's an error. Then we do a vulk load instance. So now we can use the instance level pointers. We do a glfw create window surface. So we're going to get that instance. We're going to put our window pointer in there, and we're going to get this surface out. We're going to output this surface. Then we're going to create a while loop. Basically, what this is checking for is if you do an exit event, it'll check that. And if it sees the exit event, it'll end the loop. And then we're just going to poll our events. If you don't poll the events, then the window is not going to close correctly. Like if you hit X in the top right, or if however you close your applications in your operating system, it won't work correctly if you don't have this. Then we're going to do some cleanup. We're going to destroy the surface that was created with the instance, close the window, and terminate glfw. Now, let's just build and run. It looks like it's working. Now we're going to start searching for graphics cards that we want to use in our application. So we're going to create a VK physical device variable. And what we're also going to do, if I scroll down here, is we're going to set a variable called physical count. And then we're going to have this function that enumerates through physical devices. The first call to this function, if it's provided with null at the end like this, gets how many physical devices there are. So in this case, we're reading from the instance, we're getting how many physical devices there are and putting it into physical count, the variable. Then what we're doing, and what we really should be doing, is something like this. Then we have the VK enumerate physical devices again, and this time what it's doing is actually getting the devices. And below that, we have our for loop. So what I didn't mention before was that when we created the window surface up here with glfw, create window surface, we have to, it makes sure that an ICD is found. An ICD is an installable client driver. It's the actual piece of software provided by your GPU manufacturer that contains the real implementation of the Vulkan API. And what this loop is doing, it's looping through every physical device, the hardware slash ICD found by the Vulkan loader. And the VK get physical device properties acts as a request to the ICD driver to reveal the hardware's identity. It fills the VK physical device properties structs with data like the device name or the device type or the API version. And here you can see we're looping through all the devices. We do the VK physical device properties, and we print off the name, the properties of each device. We look for a device with VK physical device type discrete GPU. This refers to a dedicated graphics card with its own VRAM. And we want that because GPUs like this are typically faster at rendering. And let's build and run again. And you can see in the output of the program that we printed off every GPU, every device. And we can see my graphics card here, my AMD Radeon RX 660, and we can see LLVM pipe. So what LLVM pipe is like a fake GPU that runs on your CPU. So like instead of sending your SPI-V shaders and vertex data to a physical graphics card, and I know I haven't mentioned that SPR-V, SPR-V stuff yet, but just listen to this part and I'll eventually get there. Maybe in another video. So I'm going to read this again. Instead of sending your SPIRV shaders and vertex data into a physical graphics card, the Vulkan loader sends them to a library, part of the Mesa project. This is in the case of you running Linux, that the LLVM, a compiler infrastructure, to turn those shaders into x86 machine code. Your CPU then executes that to draw the pixels to your system RAM. And let's change this so we only print off the device that is going to be chosen. So I changed the printf statement to being inside of this if statement. I'm going to make clean and make and run. And we can see that now we just see the output of my graphics card and not the CPU as well. All right, so let's get into queues. There are different families of queues. This is because there's different parts of the GPU hardware that are wired differently. The cool thing about queues is they have asynchronous execution, in-order submission, and cross-queue dependence. You don't have to create a queue. They already exist in your device. You just have to ask for a handle to one after you've created your VK device. Queues are grouped into families. This is because different parts of the GPU hardware are wired differently. You can handle one queue at a time or multiple queues at a time. If you want to handle one at a time, use VK sharing mode exclusive. This has maximum performance. The GPU can use the most aggressive memory optimizations. If you want to use more than one queue at once, you're going to use VK sharing mode concurrent. All right, so now I'm going to add another global variable, a uint32 type that is graphics family queue. I'm going to scroll down here. And we are going to go through, I'm going to delete that. We are going to go through our device queue family properties. So here I'm setting a queue count, which we haven't got yet. And when you run this function the first time, this VK get physical device queue family properties, it does the same thing as this function did up here. Is it sets the count of, it tells you how many device queue family properties there are, and that's what queue count gets filled with. So then we set our queue properties struct with the size of queue count. we do a VK get physical device queue family properties again, and this time we fill in all of our the properties here, and we ask for them by not having null here. Then we loop through all of our queue family properties. And what we're doing here inside of this for loop is we're trying to find a device surface that supports presentation. And if it does, it's going to set this presentation variable to true. We're also looking for a queue that supports graphics. So we're looking for a queue that supports graphics, a family queue that supports graphics and presentation. And once we find that family queue, we're going to set our graphics family queue variable to that index, and we're going to say we found it. All right. So now what I'm going to do is I'm going to fix this a little bit because we have to define this over here like that. And it's a redefinition of I, so I'll just, because there's an I above, I'll just use the same one. And what I'm going to do here is say if it was not found, then let's print error could not find compatible family queue. Return 1. And let's build and run it. There we go. If we want, we can just print off the queue, I guess, if you really want to know. So printf found family queue. Oh, there we go. And do graphics family queue family. So we know, there we go. We found a family queue at queue index of 0. So part of the issue with doing this loop is that sometimes not every every system you're working with is going to have graphics and presentation in the same queue. So with Windows and Linux, as far as I understand, is that this is the case most of the time, but there is a chance that this wouldn't be the case. So keep that in mind. I'm keeping it simple for now, but if you notice this isn't the case, you might have to change your code. So this is another warning here. And because we have a graphics family queue that has graphics and presentation, that means we can do the VK sharing mode exclusive, and that's what we're going to do in the future here. So that is going to end the video. We are eventually going to use this queue. We're going to eventually get things on the screen in the window. We're going to draw stuff to the window, but just be patient. I wanted to go through this stuff, and I don't want to just have a bunch of code and not explain what's happening. I want to do little bits of code at a time and then explain, and little bits and then explain. If you're just writing out tons of stuff at once and then you explain, I think you need, little bits and then explanations. So yeah, that concludes the video.